Well, I had another question about physics. I'm glad Jake is here. I can
Yeah,
possibly
really.
maybe Phil, something from Wallace that might help.
I haven't read Wallace since Hittinger's class.
I
That's
got
for
I
comps.
got an hour, so
Okay, cool.
yeah.
I don't think it'll take that long.
I
Maybe.
I picked it for comps because I knew nobody was going to ask me about it.
Okay. Well, shit. Because I'm wondering if the answer that I'm looking for isn't somewhere in there.
Well, what's the question?
So, um, well, I guess I'll try to state the question first, and I'll try and give you the reason why I'm thinking about it. Because there's sort of maybe other questions in the background. I want to know. I've been looking a little bit, or really, I've just been listening to lectures by and about the guy Penrose, who won the physics Nobel Prize in 2020. So his project, uh, apparently, the arguments are way beyond me, but apparently his project has demonstrated that Einstein's general relativity necessitates an actual singularity in the center of a black hole, which by all, well, that would be at the most absurd level, it would be a infinitely dense point of mass that occupies no space. And it just can't be real. It could perhaps occupy some space, but nonetheless, it has to be infinitely dense, and all of these are problems. So, like when Einstein, as far as I gather, when Einstein was first like working out his theory of gravitation with the sun, he had like a singularity there, but it was some sort of placeholder, and it wasn't supposed to be something real. And in fact, he thought there's just no way it could be real, and it led to all sorts of other developmental problems. But it seems to culminate here now, where his theory breaks down. That it seems to require that black holes have a singularity, an actual one, a real one, and that's just not possible. So he
Is
sort
the
of like
def-
reached the limits of his theory. Go ahead.
I was going to the definition of singularity is an infinitely dense point.
I don't think it has to be a point, but it has to be infinitely dense. Infinitely
It's
dense.
thing,
I don't even know
entity.
if I want to use. I don't know what the right word is. It's got to be an infinitely dense mass. I think that's
Okay.
probably the word.
Okay.
So anyway, that's got me thinking about the other sort of physics theories and how they broke down in individual places, right? So I don't know that this is right to criticize Ptolemy for this, but Ptolemy's work works um, from a geocentric point of view, right? He can do all sorts of things, and then it turns out like his assumption is wrong, but that doesn't actually mean that his theory doesn't work. Like he can still navigate you along. He can still predict accurately celestial events, etc. Newton comes along, and other people who come up with a newer theory and a better theory that explains everything Ptolemy was trying to do, along with other things. But then Newton's theory breaks down. It's not able to explain everything. So, like, Newton's theory works perfectly for certain objects of certain mass, right, at certain speeds. But then you get, like, too close to the sun, like Mercury's orbit, and it can't do anything with it. Or you get too close to the speed of light, and Newton's theory just breaks down. And similarly, we're seeing Einstein's theory break down now. Okay, so I'm wondering, I guess, first of all, do people think, not us, but do people think that Aristotle's theory has a similar breaking point? If so, what? And if not, which I would think that at least, if perhaps in some respects Aristotle's theory breaks down, I don't think in all respects. So, like, for example, somebody might look at Aristotle's theory and say, well, look, he concluded to concentric spheres, and obviously that's false. So isn't that quite like the way the theory of relativity concludes to an infinitely dense mass, which is obviously false? Doesn't that mean a mistake was made somewhere? Well, I think with Aristotle, you can say, yeah, sure, maybe an observational mistake, or maybe a false assumption, that we wouldn't have made if we had better instruments to study the stars, or if we'd already been out in orbit or something like that. And you could still maintain, I think, in Aristotle's physics his principles. Like you drop concentric spheres, drop the claim that the celestial bodies are incorruptible, maybe even drop absolute place, and perhaps you still got like hylomorphism at least, right? And a number of other principles from his physics that are, I think, still going to work. Whereas it seems like for Einstein, his whole theory is going to terminate in this point, which is like a reductio ad absurdum argument that somewhere a mistake has been made, but the mistake would either have to be in some sort of observation, like for Aristotle, or it would have to be in the calculus, right? Which I really doubt that they're making mathematical mistakes at that level. So I assume that there's actually a problem with the theory as a whole, similar to the way there's a problem with Newtonian theory. Even if it works with a certain frame of reference, like how Ptolemy's astronomy works within the reference point of a geocentric universe, it has like certain limitations under which it's able to work, but cross the limitations and it stops working. Mm-hmm. I think Einstein's theory is ultimately going to be the same. So anyway, the question is, go ahead.
Is your reason for saying that because of this infinite density thing?
Yeah, an infinitely dense mass.
Do
you think that's possible?
Well, I don't think that the term density, it refers to how tightly together different matters are in a single space, right?
Yeah.
Right. So
eventually the surface of the matter particles or whatever constituent parts you have to collide, right? They can combine, I suppose. But at a certain point, you're going to reach like a termination. Like you can only pack hydrogen together so much until it becomes helium, right?
Well, I mean, I guess with black holes and singularities, the reason that you have that is because of the way different stars die, right?
Right.
So it's like if you have a star like the sun, right, that dies, what happens is that when its core becomes unstable, right, because it runs out of fuel, the interior pressure from of the inner core starts to actually beat out gravity, right? Because it stops fusing hydrogen and starts fusing helium, right?
Well, it can fuse all the way up. The core can change all the way up into iron, which can't.
Well, stars can. The sun can't. The sun won't be able to do that. Our sun won't be able to do that, but certain stars will. That are heavy and hot enough, but the sun is not.
Oh, okay, all right.
So that's why the sun will expand into a red giant, right? Okay. And then that layer will kind of go out, and then that's not a supernova, and then you're just left with whatever's in the core, right? And that's going to be a white dwarf. Like that's what's left over. So that's one way a star dies. Another way is if you have a bigger star, right?
Yeah. Okay.
If you have a bigger star, when it runs out of fuel, it'll go through that same process of stopping burning hydrogen, starting to burn heavier elements, right? But because you're dealing with a bigger star, the gravity of its the force of gravity that's pushing from the outside is so massive because of the massiveness of the star that the winning that the sun would do in the red giant scenario doesn't happen, right?
What'd you call it?
Actually,
the winning. What'd you call
it? The winning force, like the winning.
Yeah. Okay.
So it's actually the case that the star will still collapse under the force of its own gravity because the core is unstable, and then it starts to collapse really fast, right?
Right.
and then when it collapses, it gets to the layer of the core, and when it gets to the core, it bounces out, and then it stopped at the layer of the core, and then the clapback is a supernova, right? So that's for bigger stars. Bigger stars with supernova because the surface of the star collapses to the core. The core stops the collapse, and then it bounces. That whole thing, that whole process of collapsing inward gets bounced out, and that's a supernova. So that star explodes, but then you have something left, actually, right? You still have a core left, but because the star was so massive, the force of gravity so strong that when the force collapses into the core, the elements inside, they don't fuse. It's actually stronger, right? You don't actually fuse elements anymore. You fuse subatomic elements. In fact, you fuse protons and electrons in the core.
Neutron stars.
And that's what you get. That's what gets you a neutron star, and it's super dense because you're squishing all that subatomic mass, so subatomic particles, into the space of the core, and it has like the same density or the same mass of the supermassive star that it came from.
Right. Yeah. Yeah.
But it's like the size of a city now, the core, right? So it's super gravitational. Like it's amazingly dense, right?
Yeah.
But what happened there was that the force of the collapse was so strong that it not only overcame the force that prevents atoms from fusing together, it overcame that and made protons and electrons fuse together into neutrons.
Yeah.
And that's what you're left with a big ball of neutrons, right? That's what it is, right? Now, that's another scenario. But when you're dealing with a supermassive star, right, that you have that same collapse, gravity wins that fight, but the collapse is even stronger. So instead of smushing into a ball of neutrons, you smush into a point. Like you just...
At least that's how the mathematicians have thought about it, that it swishes to a point. Though there was a lot of debate about it, too. It can't be a geometric point, can it?
Like what's left over, I think what's the collapse goes in reality.
Say that again?
I think that, so, like, this is the core, right?
Yeah.
Of a star that will be a neutron star.
Yeah.
When you have the collapse, it'll go to that point right here, to the core, and then it, boom, collapse back out, and then you have a neutron star, this thing right here, right? But with a supermassive star, you don't just have the core, but that also crumbles too. So the collapse just keeps going and going and going, and the core crumbles, and you're just left with this point. So the collapse converges to a point.
Yeah, but do you think that this point is a real object or a mathematical postulate so that we can, like, think about or make this is how, like, our gravitational theory would try to explain this sort of event? Because I think that's the way Einstein took singularities. This is why Penrose's paper was such a big deal.
Well, I mean, I don't have a problem with mathematical points existing, if that's what you're asking.
But do you think that matter can condense down to a point that is a lengthless, breathless thing? Like they literally describe it as the end of space, right? That there is no space occupied by the singularity.
I don't know if it's literally that or just something effectively that small.
Yeah, what they sometimes say is that it's a point which tends toward infinity or something, to avoid using the word actually infinitely dense. It's just unimaginably infinitely dense.
Yeah.
Or tending towards infinity as to its magnitude. And they sometimes say that to get around it. But Penrose seems to have shown that the only way this happens is if in the math it's a geometric point, like an actual one, a real existent geometric point in which the matter of the star has been compressed to an infinitely dense, lengthless, breathless space.
Something that has no dimensionality.
As far as I get it, I could be wrong. I'm just listening to lectures and trying to follow. But then there was this other weird thing that I heard in one lecture where somebody was talking about a ring-shaped singularity, and I didn't quite get what that is. But the thing they've always been trying to explain is Einstein first put out this theory about the gravity of stars, and then somebody asked, what happens if the star is so massive? Oh, sorry, backing up. So Einstein put out this theory about stars, and there was this like ring that was worked out inside the star. What was it called? It was named after some German guy. I'm trying to remember exactly what it was. At first they called it a singularity, but of course it's not. Today we call it the event horizon. But in stars, it was understood by Einstein this would always be inside the surface of the star, and so if you want to use it as a mathematical postulate, it doesn't matter because it doesn't affect nature. You're never going to see it or measure it. And in fact, he, I think, tried to prove in his equations before black holes were discovered that there cannot be such a star which is so massive that this ring of gravitational pull out of which no light can escape would extend beyond the surface of the sun or the surface of the star. It would always be contained in the surface. And then later on, we discovered that there actually are such massive objects in space that occupy so little space on their own that this sphere surrounding the core, out of which no light can escape because the gravitational pull is so strong, actually is outside the core. It's not the same thing as the black hole. It's something outside of it, where the gravity well is so strong that not even light can escape. Einstein thought that would have been a problem for his theory if such a thing was real. It turns out it actually is real. And so that's what got everybody asking questions about singularities and whether they can actually be real. And at first people thought that it wouldn't be, that the theories which showed that it would in fact collapse to a singular point always assumed that a star was perfectly spherical. And so as the core collapses, they would all collapse directly inwards to the center of mass, which would, of course, be a point. And they were saying, well, actually, no, stars aren't perfectly spherical. So at the very end of things, the final moments of the collapse, surely some of the particles would miss each other and it would at least occupy a minimal amount of space. And Penrose, in his paper, showed that actually it doesn't matter what shape we assume the star to be, it will always collapse to a point if the math is right.
Yeah.
And that's, well, I don't know. I mean, it seems to me that both of those are problems. Infinitely dense seems to be a problem.
I don't think that that's a problem. I mean, because, if you just took my mass and condensed it to a point, it would be infinitely dense.
Yeah, right? But that's...
I don't understand how that would be so... Why that would be so...
because it's a point, because of what a point means.
Yeah, it's not because of the subject from which you get it. It's because of the...
It's not incoherent. Like, I can imagine it, but I don't think that reality could sustain such a thing. I can't imagine it being real. I can think about it, and it's not incoherent. Right? That's what they mean when they, like, the math proves this, right? It's obviously not incoherent, but could it actually happen?
Infinite density?
Yeah.
I think so. I mean, it's infinite density is not infinite power from a material thing. Like the force, the gravitational force, even from an infinitely dense singularity, is still finite.
Well, actually, I think that's part of the problem, is that in order to explain the event horizon, the gravitational pull within that space has to proceed toward infinity in order to actually trap light.
I don't think so. If light is a finite velocity, then you wouldn't need... You just need a stronger force than light to trap light, which wouldn't require... It would just require a greater force than whatever, 300,000 kilometers per second squared.
Yeah, I mean that makes sense when you say it. I think there's something about light and light speed in Einstein's theory which sets certain limits on reality, though, right?
I know that for physicists in general, the speed of light being a limit of material speed is important.
Mm-hmm.
It's like, so nothing can, in actuality, be faster than the speed of light.
And why is that exactly? Do you know?
I guess, I mean, I don't know exactly why, but it's sort of the same reason why. The way I understand it is like animals have a certain size limit. Like you can, if you're going to be a land animal, you can only be so big because physics will stop the the biology from
Right.
exceeding a certain capacity. There's just a biological limit of size, right? Um, it's like you can imagine, a 5 billion ton giraffe, fine, but it's like you're never going to get that because if you make a giraffe bigger, then its head is going to collapse under the weight of its neck or something like that. Whatever. It's something like that. Um, like you,
Yeah, yeah, sure, I get that.
it's like light, like for matter to move, things have to go together, right? And if certain things have to go together, and if you're going to have matter move quickly, those things have to go together well, and that can only work up to a certain point. Like
Sure.
something in the equation stops working, like the matter disintegrates, or I don't know what.
Yeah.
Uh,
Yeah, and I guess it's true that light can be affected by gravity that is not infinite,
mhm.
right? So we see light bend around massive objects.
Yeah.
Uh, to trap light, though, there is, I mean, I've seen this over and over again, so I know there's something here. I just don't know what it is. There's something about actually trapping light that breaks the system.
What do you
That
mean?
requires this infinite density. Because this comes up in all of the videos and lectures I've seen. Um, this was a concern of Einstein, right?
Uh-huh.
Um, so I don't know. Like, because what you're saying makes sense. You would think that you don't need an infinite density to explain this. Like, why can't the math just use a density that's just enough,
Yeah.
right?
Yeah, I mean, well, you don't need infinite density to explain it, or even if you have infinite density, which in theory is, I don't think is horribly problematic. Infinite density doesn't mean infinite power,
Right.
which is, I think people confuse the two. It's like, oh, infinitely dense, it must be able to do anything. I can trap light. My gosh.
Well, it really goes back to the
Yeah,
point thing, right? Because, like you said before, we could contract any of our matter down to a geometric point, or really the matter of anything down to a geometric point. It would have to be infinitely dense.
right, exactly. Yeah.
But, oh, what was I going to say? Oh, yeah. But, like, do you think that matter cannot occupy space?
Matter cannot occupy space.
Would you say that a geometric point in reality occupies space?
Uh, it's it's um
It's a lengthless, breathless.
Yeah, I mean, it
Yeah.
doesn't occupy space because it's
Yeah.
not. I mean, you need a body to occupy space.
You're right. Okay. So,
It's represented in space.
yeah,
It
yeah.
doesn't
Okay.
occupy space.
So the problem is, and why it seems inconsistent to me, is that we're taking bodies and compressing them down to the point where I suppose they can't be a body anymore because they only occupy a point. Right? You take the mass of the star that collapses into a black hole and you compress it down to a point. It was a body before. Is it still a body? Does it still occupy space? If it does, it can't be a point. If it can't be a point, it can't be infinitely dense.
Yeah, so that, I mean, that's I think it's still technically a body, just indefinitely small, and
Well, indefinitely small, does that mean a point?
I mean, effectively, yeah.
Effectively. I
I,
want to. I think this
well, like
matters, you know.
astronomers aren't geometricians. Like they're not the same thing, right? Like you're using geometry in astronomy. Sure, it's a subalternate science, yeah, but like you're dealing with actual bodies now, right? So it's like um, I don't know. It's wh- just like for like for the logician, what a man is, and for the biologist, what a man is, like you're not going to have the same account,
Hmm.
right? Because uh, the biologist actually considers the thing first, right? So
Yeah.
he might look at someone with one arm and say, well, technically in the definition of man, you've got something with two arms, but that's a man, right? Um, it's like that. Like it's close enough. Like when you're
It's a
dealing
point
with,
analogously.
huh?
You want to say it's like it's a point analogously.
Yeah, it's a point. Well, not analogously, but close enough. It's so small. It's so small that it's effectively considered a point.
But I,
I think that the premises used by Einstein and which Penrose draws to their conclusions, just from what I understand, only works if it is an actual point, not an approximation. They've often said before Penrose here that it can't be an actual point. Like surely it's something approaching infinity or something, but and they tried to work out how a star could collapse so that it wouldn't produce this singular point. And then Penrose seems to have upset
and
all.
they mean by point the geometric point that
Yeah,
has
like
no
they talk about
that's
like
no
a black
space.
hole in space, right? It is not space. It's
Hmm.
the end of space.
That doesn't mean anything to me.
Well, like how a point is at the end of a line,
Hmm.
right?
So, and your point is that if anything has existence, then it has to have some dimensionality, no
If
matter how small.
material things
Yeah,
exist, yeah, then I think it
and
has
therefore
to
it
have
can't be a point.
dimensions. Yeah, I think it's reductio ad absurdum for
Yeah.
Einstein's theory in the same way that like the orbit of Mercury was in a reductio for Newton, right? It
Hmm.
just this theory broke down at that point, and it had to be replaced by something newer or more comprehensive or something like that, right? So people say that maybe a quantum theory of gravity will be able to explain the singularity problem in different and more perfect terms. Penrose, for reasons that I cannot understand, is not optimistic about that. But quantum theories have their own problems, like the measurement problem and stuff that we don't need to get into, which seem to me like reductios against their own work. But anyway, really, like I don't really like this is an interesting way into the discussion because it seems like there's this sort of thing happening in physics where we start with maybe an assumption or a model or perspective or whatever, and we work out math that explains phenomena from that perspective or from the work of that model. And then we reach a sort of point where it stops working. It works perfectly within the model, and then something sort of outside the model breaks the model, and we need to replace it. Physics seems to do this over and over again. And I guess at bottom, I'm wondering why you think that would be, and why you think Aristotle's physics doesn't do that. Like, what's the difference between the work of cosmologists today that require them to kind of advance a theory until it breaks, replace it, advance a new theory until it breaks, replace it, advance another theory until it breaks, replace it, right? Why is their work having these sort of waves of progression whereas Aristotle's doesn't. Certainly, I guess you'd say first that Aristotle's, of course, building on the back of Plato and other thinkers, and he certainly looks back on the pre-Socratics and he's like, all right, this is what they got right, this is what they got wrong, this is where their theories break, and here's mine. He does something similar in that respect.
Well, what theory are you talking? Are you talking about Aristotle's cosmology, or what exactly?
I suppose his physics in general, so including his cosmology, certainly.
Oh, well, I mean, I think that you can't say Aristotle's will break down, because all it relies on is an ordinary experience of nature, and making syllogisms from the observations collected from an ordinary experience of nature. After that,
yeah, and proceeding from abstract definitions and, as far as possible, avoiding particular conclusions.
Well, no, I mean, okay.
There's there's what I have in mind is in the metaphysics, where he's considering the number of separate substances, and he offers two possibilities depending on a different way you want to slice the sky, or something like that, right?
Uh-huh.
So he sort of restrains himself,
Mm-hmm.
recognizing that if you look at it this way, it's going to be this number. You look at it that way, it's going to be 55 or whatever.
Mm-hmm.
When he gets down to like those particulars, recognizing that it depends upon an observational fact, which may or may not be correct, he sort of, at least there, has a clear answer. So,
yeah.
Like, I think if Aristotle's physics is approached with that sort of restraint, I think you don't run into these sort of problems. And I kind of want to compare it to something like this. And this is actually the reason I started thinking about this altogether. We've been going through the 5 ways in metaphysics, and one of my students is very concerned with the God of the gaps sort of fallacy.
Uh-huh.
And what I was explaining to the student was that if there was something on the roof throwing, I don't know, some objects in the air, I would know without a doubt that there is, witnessing the effect, that there's a cause on the roof, that whatever it is such that it's able to send these bricks in the air precisely as I'm witnessing it.
Mm-hmm.
And that's the sort of restraint that I think Aristotle's unmoved mover argument has. Whereas maybe, and this is what I didn't get into with the student, but what I've been thinking about, maybe what the modern cosmologist wants to do is not just like put in, X, where X is the cause for whatever effect I'm seeing. They do that too sometimes, like with dark energy and dark matter. But what they try to do beyond that is they try to hypothesize about what could be on the roof throwing these projectiles. And so they build like a model, and they're like, what if what's on the roof is a trebuchet, right?
Mm-hmm.
And the trebuchet seems to be the way the projectiles are flying just well enough until we find one projectile that just doesn't quite fit the model, and then we have to revise the model to fit the new data. I'm wondering if I'm thinking about the difference rightly. That Aristotle is sort of restrained in his conclusions. Obviously, he concludes a lot, but he doesn't conclude more than he can from, as you said, the common experience.
Since those are all quia arguments,
mm-hmm.
you're coming to the existence of a cause based off of the effect. Then all you can say about the cause, the nature of the cause, is that its nature is such that it's able to produce that it has power that's able to produce the proportionality of the effect that you witness, right?
Right.
But since you're talking about universal effects, then you're saying as much and as little as attributing a universal cause and power to the thing that you're saying. So I mean, you're saying a little, but you're saying a lot too, right?
Right. Sure. Yeah.
So. Yeah, I mean, Aristotle knows what he knows, and he knows what he doesn't know. He knows when he's making an assumption, and he knows when he's making a demonstration. Like the thing that comes to mind, like about the breakdown of his theory, it's like, um, you're I'm never going to experience nature in a new way that doesn't that convinces me that matter isn't continuous. You know what I mean?
Right.
That's never going to happen. Um, so all the conclusions he has about motion, how you need a body for motion, a mobile body, and that depends on the divisibility of matter, continuous matter, like all that stuff. That's never going to change because he's again starting from square one. It's like things are moving. The things that are moving have a beginning and an end, and things like that. Um, but the observations in the models and the theories that people that really wise, intelligent thinkers have contributed, those do break down, right? You can look at Mercury as an ancient observer difficultly, but with that, you're not going to with just the power of your eyes, you're not going to really see a problem with its orbit,
Right.
right? But later, when you have a new experience of nature by being able to perceive more closely how Mercury is moving, then you're going to see this like kind of swinging thing.
Yeah.
It's like that's not how. Okay, that's a new experience of nature for me. One that wasn't accountable. That one that I didn't have to account for according to the old model because I couldn't see it according to the old model, right?
Right.
You're not going to have anything like that with Aristotle's stuff. Like it would be as far as saying like things don't act for an end. Like, okay, give me the experience of nature that shows me that, or or matter isn't continuous. Like, give me the experience of nature that tells me that, or things aren't moving. Things give me the experience of nature that tells me that, right?
Yeah.
Those would be the things that you'd have to break down to say, okay, well, that would lead to a breakdown of the theory, right? Give me the experience of nature that shows me that the part is greater than the whole.
Right. Right.
It's like, well, that's not going to happen. You're not going to show me any of that.
So, what you keep coming back to is the common experience that we have of nature, right? And because
Mhm.
Aristotle's theory sort of works within that framework, it's never going to be disproven because it's a perfect account of the common experience of nature. But like when we take the elliptical orbit of Mercury,
Mhm.
yes, it's not part of the common experience of man. It needs a telescope and careful measurement to detect. Let's say. Does that mean that Aristotle's theory won't account for that, or that like when somebody says that the continuous quantity of my desk is actually the electromagnetic connection of all of its atomic particles, like does that mean that Aristotle's theory stops working there? Sorry, I'm getting a Discord call on the. Let me just hang that up. It's ringing in my ear.
Mm.
At those points, like where we're beyond the common experience of nature, when we're dealing with things that like Coons was trying to deal with, and Phaser recently was trying to deal with, and what's the guy who interviewed at the center when we were there? The guy that shoot, is he an old TAC guy? I think he's an old TAC guy. Does a lot of cosmology stuff. I'm gonna say like
Yeah.
that guy.
He
Is
looks
there a
like the
whole
government.
project?
Yeah.
Yeah,
I know what you mean.
you got. I know you've got a guy. I couldn't remember who the guy was.
He
He's supposed
looks
to.
like the FBI guy.
Yeah.
Yeah.
I want to say like it's Nesbit or something, but I know
Yeah,
that's not it, but
I don't know why I
it's
can't remember.
Brungart.
Yeah, Bernard. Yeah.
it sounds like Nesbit.
Do you think that their project is totally like sort of doomed because they're taking observations which aren't common, which require precise instruments or something to to get to, or do you think that Aristotle's physics could, at least in some way, be applied? Because I would say, like, for example, we're not going to hold to concentric spheres as an accurate cosmology anymore.
Mm-hmm.
But like the planets, can I imagine them moving through space in the Aristotelian way? Yeah, I think so. Can I talk about the transition of one star to a different type of star in the Aristotelian way? I think so. I could even talk, I think, about natural place in a certain extent with the current solar system model. So,
Heck yeah.
yeah, so like it doesn't seem like even with uncommon experience that the theory actually breaks down.
Right. Yeah. You mean Aristotle?
Yeah.
I mean, certain aspects are going to have to be disputed, right? Like Aristotle obviously holds to concentric circles.
Certain remote conclusions, it seems, right? Where this, what we would do is instead is take the premises, them being the same, apply them to the new observational data, the new experience of nature, and then derive new conclusions. Right? Like you're not going to conclude to the concentric spheres anymore.
Mm-hmm.
I mean, that's what I would say. That like we're going to reject some of the conclusions of Aristotle because observational data is newer and better, but that the premises themselves, the principles that he puts forward in the physics, those hold, and they're going to be just as applicable to the new experience as it was to the old.
Right. Yeah.
Okay. I thought you were saying that the reason why Aristotle's physics hasn't suffered a similar breakdown is because he wants to restrain himself to common experience, and because there's no contrary to fact condition to the common experience, right? It's just there's not an example of matter which is not continuous to consider, right?
Yeah. I mean, that's the point I was making, right? I mean, he's being a careful scientist, and he's doing philosophical science, which relies on common experience of reality, and making abstracting universal principles from those common experiences of reality. And if the common experiences still hold, then the principles abstracted should therefore hold.
Yeah.
And I think that's just what it comes down to. I'll quickly hang up my Aristotelian hat when I find a part that's rare in the whole. I'll do it.
You might have to hang up your whole freaking brain.
Yeah.
But yeah, sure. Well, cool.